Welcome. In this video we are going to see about Vlsi Design Introduction. Myself, Mrs. K. Karpura Sundari, working as an assistant professor in EC department from K. Ramakrishnan College of Technology, Samayapuram, Trichy. So in this unit, in this syllabus, the following topics are going to cover. So the first unit will cover about mass transistor theory, and in second unit we are going to see about combination logic circuit, and the third unit will describe about the sequential circuit design and subsystems. Fourth unit will covers designing arithmetic building blocks and Vlsi HDL, and fifth will describes about the implementation strategies. So if we are taken a first unit, in that we are going to see about various transistor theory involves in terms of metal oxide semiconductor. So in that we are going to see about ideal characteristics analysis as well as DC characteristics analysis, as well as the various analysis carried out in the designing the transistor. And the second will carries about CMOS logic design for a combinational circuit that describes about the various pass transistor logic. And in third unit we are going to describe about various flip-flops and latches that we are designing by means of using the CMOS design. And the fourth unit will describes about the various arithmetic design that we have to carry it out by means of using a digital design techniques, and the design techniques will be carried out by means of using a hardware description language. So this unit is fully about the Vlsi HDL. And the fifth unit describes about the various implementation strategies, that is various strategies needed in order to designing an IC, especially we can also call it as a FPGA, that is programmable logic and non-programmable logic, that relies on the ASIC design and FPGA based designs. So those are the things that we are going to see in this syllabus. In the first unit we are going to see about the mass transistor theory. Under this we are going to see about MOS transistor introduction, long channel IV characteristics, non-ideal IV characteristics, DC transfer characteristics, and a CMOS process design flow, layout design rules, gate layouts, stick diagrams. So in this video we are going to discuss about the following contents: IC evaluation, common technologies, CMOS transistors and logic gates, Vlsi design process, Vlsi trends, market scenario, and various semiconductor products which is used in the market under an overview. So first we have to know what is ICs and why we made IC. So we all already know IC, an acronym is integrated circuit. So using that we can describe or we can design or we can implement various number of electronic components into a single chip of IC. The main reason why we go for IC fabrication is it will reduces the size of the particular device. So in that case alone we can come into the word called a integration. So the main reason why we go for a integration means it will improve the size, speed and power of processing. So if you are taken an example of a day-to-day life, in that whatever the device that we are using from the past to present scenario, the size of the device is very reduced one, that is miniaturized one, and the speed of the device is also improved, and the power of taken for the particular device is also gets reduced. And this all the things will be based only on the size of the particular component, not a component, it is a device. And the second why we go for integration is in order to reduce the manufacturing cost, so that this will lies on the automation. That is, the automation will be based on how far we are doing the fabrication process for fabricating the integrated circuit. So if we are need to reduce the manufacturing cost, there also we need an integration. There the integration describes about the automation, and that automation will be done by means of using electronic design automation tools. Various tools are involved in Vlsi design in order to fabricate the particular FPGA or a programmable IC. So almost if you are taken the if you are need to reduce the manufacturing cost, that the manual assembly is not needed. If we come into the IC evolution, 1 second. If we come into the IC evolution, we can also classify the IC evolutions into various categorization. One is small scale integration, second one is MSA, that is medium scale integration, third one is LSA, large scale integration, fourth one is VLSA integration, that is very large scale integration, and ELSA, ultra large scale integration, and so on. And based on that, we can also call it as what is a small scale integration to a micron as well as nanotechnology comes in there. So if you are taken SSI, there the number of logic gates present within the single chip of IC contains 1 to 10, and if you are taken a medium scale integration, that will be in the range from 1 to 100, 10 to 100, and if you are taken a logical functions and counters, that will come under the LSI. In that LSI we can have 100 to 1000 number of transistors, and if you are taken VLSI, we can have 1000 to 10,000, that is more than 10,000 number of transistors, and if we come into the ULSA, more than million number of transistors will be involved, and so on. And if we have taken a CMOS logic, in that also we can classify the IC evolution into various categorization. One will come under the bipolar technology, second one will come under the metal oxide semiconductor technology, and third one will come under the BiCMOS technology, fourth one will come under the gallium arsenide, and the fifth one is silicon germanium technology. So various technologies were involved based on the transistor based CMOS technology, MOS technology evolution. And if you are taken a bipolar technology, there we can classify that into transistor logic and emitter coupled logic. You all already know what is transistor logic and emitter coupled logic. And if we come into the MOS logic, that can be invented before the bipolar transistor, and the main drawback of this kind of transistor fabrication is the difficulty during the manufacturing is more. From that MOS technology alone, we come into the NMOS and PMOS technology. So if you are taken a NMOS technology, there the speed of the particular transistor will be in a controlled manner, and if you are taken a PMOS technology, power consumption is also gets increased. So in order to avoid the drawback of PMOS and NMOS alone, we go for a complementary semiconductor technology. So in that we are integrating both the N channel and P channel MOS transistor, and that will reduce the power consumption and simplify the fabrication process, and that will increase the speed of propagation. So that only using that MOS technology we are achieved the power consumption as well as speed of transmission. And next is a BiCMOS technology. Compared to the CMOS technology, that the speed is somewhat less compared to that of the BiCMOS. So that here what we are going to do means, in bipolar technology, we all already know what is bipolar technology, what is the main advantage. So if you are taken a bipolar technology, the speed of processing is more, but the power consumption consumed in the transistor is very high. So here in BiCMOS, what we are going to do means, we are going to improve the speed as well as the power consumption. So in order to increase the speed, here we are using a bipolar technology, and in order to reduce the power consumption, we are using a CMOS technology, and both will be combined together, will be called as a BiCMOS technology. This is especially for high speed integration. And another one technology is gallium arsenide technology, and this is also involved for high speed applications. And next one is a silicon germanium technology. Using that, we can improve the radio frequency applications. So we can have various types of silicon manufacturing alternatives available. One is based on the standard components, and the second one is based on the application specific ICs. So if you are taken standard components, that is based on the FPGAs, and if you are taken application specific ICs, it is based on the ASIC. So if it is a standard component, it is especially used for a fixed application as well as a programmable application. Another name for programmable application is application programming. So if it is a fixed application, we are having logic families, and that will come under the TTL and CMOS. And if it is an application programming, there we can have two kinds of programming. One is based on the hardware programming mask, and the second one is based on the software programming mask. If it is a hardware programming mask, the masking will be done by means of using the external memory unit. So here we are using a PLAs, that is programmable logic arrays, and ROM, read only memories. And if we are need to do a software programming, there we are using a microprocessor, electrically erasable programmable memories, electrically programmable read only memories, and PLDs, that is programmable logic devices. And if you are taken an application specific ICs, we can classify that into a three categorization. One will come under the semi custom, second one will come under the full custom, and the third one will be a silicon compilation. So if you are taken a semi-custom ICs, there we are already having a design, and in that design, if you are need to program any kind of logic circuits, there we can use it. So it is an already that is partially fabricated IC will be present. In that we can do the programming, that is called a semi-custom. And if it is a full custom, we are need to implement whole of the design from the scratch to the 100% level. And if it is a silicon compilation, there we can do an automation process in order to fabricate the design. Then now we are going to see about the VLSI technology, which is based on the CMOS transistor. So we are having two kinds of transistor, as I already told you earlier. That is, if it is a CMOS, we are combining both the N channel and P channel MOS transistors. So if it is a P channel MOS transistor, what we are having means we are having a channel in between the two P substrate. So that channel will segregate your N substrate as well as the P substrate. And in that, if you are need to provide a connectivity, there the interconnection are made by means of using a polysilicon gates, and the channel will segregate your P channel and the N channel, or separate your P channel and N channel by means of using silicon dioxide insulator, so that we can avoid the unnecessary short channel effects that happens between the P substrate and the N substrate. Normally, if you are taken a MOS transistor, it contains three terminals. One is gate, another one is drain, and the another one is a substrate. So the substrate is normally connected to the VDD, and the input is given through the gate. So the gate is made up of a polysilicon gate, and the drain will provide the output. So if you are taken a N transistor, here we don't have any separated channel. That is, here we don't have any separated channel in between the drain and the source. So this figure describes about the what is CMOS transistor networks. So normally the P transistor will be called as a pull-up network, and the N transistor will be called as a pull-down network. If we are combining both of that, then we can get a CMOS inverter. So using that CMOS inverter, we can get the output as a inverted output of the given input. And this is the example how we can design the NAND gate by means of using CMOS transistor logic. So if you have taken this example, the pull-up transistor is present in the upside, and in the downside we are having a NMOS transistor. So if in a PMOS transistor, if you are interconnecting two number of transistors parallelly together, then it is called a PMOS NAND gate. And if you are interconnecting two N channel transistor in series, then it is called a NMOS NAND gate. If you are combining both of that connectivity together in series, then it is called a CMOS NAND gate. So if we come into the VLSI levels of abstraction, that is, we have already seen about what is integrated circuit and what are the evolution. So if we have taken the evolution, we can also do all the evolution or integrated circuit design by means of using automation. So if you have taken electronic design automation, various levels of abstractions are there. So that can be segregated into various levels. One will be a specification, second one will be architecture, third one will be a register transfer level, and fourth one is a logic, and fifth one is a circuit, and the final one is a layout. From the layout alone we can get the final implementation of a chip. So if you are taken a specification, in the specification we are going to know what are the inputs that we need and what are the outputs are needed, what is the type of logic we need to evolve. So that is described in the specification, and in the architecture we are need to identify the major resources needed. That is, we are going to describe about what is the overall architecture of the particular hardware and what are the connectivities that is needed. And the next is about the register transfer level. So in the register transfer we are need to describe about the logic blocks, final state machine, and the connection. That is, in the architecture level we are describing all the implementation strategy into a block diagram, and that block will be described in terms of any type of hardware description language in a register transfer level. So in the register transfer level we are converting the architecture into a various languages, or else we can convert that into a logic blocks or finite state machines, or else into various connections. And that register transfer level language will be converted back into a various gates and flip-flops and latches, or else a connectivity will be called as a logic. And after converting that into a logic, we can convert that and analyze it into a transistor level logic. So the transistor level logic will be analyzed by means of using a circuit. So in the circuit we can analyze its various parasitic elements and its associated transistors and interconnects. Then after that, that will be converted back into a final layout. In that we can describe that into a floor planning and back notation process. So in that we can describe what is the mask layers that we need, what are the polygons we need, and how we can interconnect the layers into a particular block. And finally that can be implemented and converted back into a final bit programming file, and then we go for a implementation strategy. So based on the various levels of abstraction, we can also going to design about the various VLSI design process. So all the design process will be evolved from higher level to the lower level, and the automation can also be done by means of using computer aided design tools. So the main reason why we go for this VLSI design process is in order to reduce the design time. We can also reduce the non-recurring engineering cost, and we can also reduce the unit cost. In order to improve the performance and reduce the power consumption also, we go for a VLSI design process. And these are the trade-offs that is present in the VLSI design. So if you are taken a power consumption, it should be very low supply voltage, and that supply voltage will depends upon the clock speed. So we can have various types of VLSI design styles, and that design styles is also categorized into 4 type of IC design. One is based on the full custom IC design, second one is based on the application specific integrated circuit design, and the third one is programmable logical IC design, and the fourth one is system on chip design. So if you are taken a full custom design, each circuit element will be carefully handcrafted, and the design effort should be more. So because we only going to design the circuit, so more care should be needed. And if the design is higher, the non-recurring cost will also be considerable one, and unit cost should be low, and that should be based only on the design engineer. And here the performance should be high, and this is especially used for high volume application. Then if you are taken a programmable logic design, here we are having a pre-manufactured components with a programmable interconnect. So the CAD tools will greatly reduce the design effort, and design cost is very less, NRE cost is very less, and unit cost should be high. The performance of the programmable logic should be lower compared to that of the ASIC based design. And the third one relies on the system on chip. So here we are having, or we are combining several large blocks by means of using pre-designed custom cores. So by means of using that custom cores, we are making that into an intellectual property, and that can be called as a special purpose hardware. And this special purpose hardware is made only by means of using the ASIC based design. And if you are need to describe this kind of system on chip based design, we can also use it or performing the design by means of using a programmable logic. So in that programmable logic we can also do the design by using PLDs and FPGAs. The main issues present in system on chip is design cost should be low and correctness of the design should be very important. And this is the roadmap how far the design fabrication that goes on based on its performance level and from the size and supply power consumption. So at present where the VLSI products are used means, if you are taken a processor, it is used for designing a CPU, that is central processing unit, then digital signal processors, controllers, all the things are designed by means of using VLSI. And if you are taken a memory chip, it is used to design RAM, that is random access memory, read-only memory, electrically erasable, programmable read-only memory. If you are taken an analog application, there we can use the design for mobile communication, especially for audio and video processing. And if you are taken a programmable ICs, so it is used to design by means of using programmable logic arrays and FPGAs. And if it is an embedded system application, these are used in cars, factories, network cards. And if it is a system on chip design, there we need to do a chip based applications. Thank you. And in next class we will see about the mass transistor theory.